to complain, but all right, good. So now we can read the title. So this will indeed be about Higgsing 5D CFTs from 3 different viewpoints, from geometry, brains, and quivers. And so all of these individually could be talked about at length. So this is not going to be super precise. I'm not going to explain everything in detail. And also, I'm just going to work with examples. And actually, I just kind of want to put together some different puzzle pieces, how they fit. And actually, the whole talk is here. This is all we'll do today. So I'll just briefly say what that is. Over here, we have a brain web, 5-brain web. Over here, we have the equations defining a Calabi-Yau threefold, a local Calabi-Yau threefold, something non-compact. And down here, we have something called a magnetic quiver. So this you can think of as a 3D n=4 gauge theory described with these nodes and edges. And we're going to look at Higgsing a five-dimensional conformal field theory. And we're going to see that this can be described in 3 ways. Once by pulling away a brain, sending it away. Once by deforming an equation with some term. And once by giving a VEF to a monopole in this magnetic quiver. And these 3 things, we'll see how they fit together. That's the idea. And okay. So before I really start, let me mention some collaborators. So many of the things that I'll say in general is either already known for a long time, or it's work done with Antoine Bourget, Ami Hanani, Markus Sperling, and Zhenghao Zhong, and also many others. And then the stuff I'll talk about in particular today is done with Maria De Marco, Michele Tuzzotto, and Andrea San Giovanni. And all of these are here, so you can also complain to them. All right, so 5-dimensional n=1 CFTs is what we're going to look at. And they can be constructed in 2 ways in string theory. And how this fits together is the topic of the talk at the example of Higgsing. So one way is to put M theory in some local Calabi-Yau 3. So we'll have an R1,4 left over. That's these are our 5 space and dimensions. And the other way is to use a 5-brain web in type 2B string theory, ending the 5 brains in 7 brains. And the 5D field theory will be on the world volume of this, which is actually 5-dimensional due to the 7 brains being present. So in this geometric engineering picture, the Coulomb branch of our theory is described by the resolutions of our Calabi-Yau threefold. And the Higgs branch is described by complex structure deformations of this threefold. And in the 5-brain web, the Coulomb branch is described by some breathing. Down here, there's a 5-brain web, and it's breathing, by some breathing modes of the web. And the Higgs branch is described by decomposition of the web. We'll see an example later. And if we're dealing with a toric Calabi-Yau threefold, then there's a very nice duality to a very specific brain web. So there are also so-called toric brain webs, and then there are others. And yeah, if everything is toric, then it's super nice to match these 2 approaches. And this is also the round that we will be in, but then leave by Higgsing. Okay, so the Coulomb branch of a 5D CFT is very easy to describe both in the geometric engineering and in the brain web construction. So we're not going to talk about this. This has been done 20 years ago, and it's really nicely understood, and it's just not a problem. The Higgs branch of a 5D CFT is not, or we could say is barely understood in the geometric engineering approach. So the Higgs branch people typically think is kind of the easier object because we learn it's classical or something, but this is just not true. This is only the case if you're dealing with a Lagrangian theory. A 5D CFT is not Lagrangian. It could maybe have a description as an effective field theory if we deform it, but it is not itself Lagrangian. So the Higgs branch is actually a super hard object because we can't use any of our field theory methods to compute it. But it is, by now, really well understood if we have a brain web. This goes via something called magnetic quivers, which I will briefly introduce, but yeah, I will not say so much about them. So the goal is better understanding the Higgs branch from this better understanding the Higgs branch in the geometric engineering picture using the intuition that we get from brain webs and these magnetic quivers. Okay, very briefly a brain web. We have type 2B string theory. Given the name of the conference, we know what that is, and we know that there is brains. I'll just say how they are fitted inside our spacetime. So we have the 5 branes, which span the 0 to 4 and the 6 direction, NS5 branes, which span the 0 to 5 directions. And then we have PQ5 branes, which you get by merging a D5 and NS5 branes. So PD5 branes, Q, NS5 branes. And they are at some angle. And there will also be PQ7 branes, which is where the 5 branes end. A PQ7 brane is kind of just like your standard D7 brane, but the monodromy is a little bit funky. But we don't have to get into the details here. So let's see how we actually construct a theory here. Well, if we take some parallel D5 branes, we would get some 6-dimensional super Young-Mills theory. Terminating this on NS5 branes actually gives us some 5-dimensional field theory. And there is, of course, the bending of the branes due to the charge. So here we constructed some SUN level 0 pure gauge theory. We can turn on the level by bending the branes a little bit, and we can also add flavor. This is all pretty straightforward. Now we know how to construct any SQCD in 5 dimensions. All right, so that's a brane system. Now, what are the moduli? In supersymmetric field theories, we always have some, or not always, but we usually have some interesting modular space of vacua, which is kind of the most basic object to study when studying any of these theories. Of course, first we want to know about the vacua. So here I took as an example SU2 with 4 flavors, 4 fundamentals, and this is at finite coupling. And the brainweb corresponding to this looks like that. And there is the Coulomb branch, which of course we won't discuss as I already said, but I still want to show it. The Coulomb branch is achieved by separating the D5 branes, but kind of along the NS5 branes. This will leave an abelian vector multiplet and otherwise Higgs the theory along the Coulomb branch. The other option is going to the Higgs branch. And here now I'm doing some modern art. I'm actually trying to draw the 3-dimensional setup, or approximating this by a 3-dimensional setup. So these are 7 branes here, and the 5 branes are being moved along these 7 branes. So I can count the number of moduli that I have. On the Coulomb branch, there's just one phase I can open up, 1-dimensional Coulomb branch, which fits the rank of our theory, that's good. The Higgs branch, here we see that we have 5 independent brane segments we can move. There is an overall center of mass we get rid of. And if you do the classical computation, this is exactly the dimension of the Higgs branch. So the branes, they see your moduli space. Now, the geometry of the moduli space is, especially here of the Higgs branch, is not yet captured. We have the dimension. It's already a start. So we will now suppress these x 7, 8, 9 directions because drawing the 3-dimensional thing is just outrageous, and we can just use colors instead to denote another dimension. So I've colored the branes over here. This stands for moving them along the 7 branes. And now if I want to know the geometry of this Higgs branch, I can extract something called a magnetic quiver, which was introduced by Cabrera, Hanani, and Yagi in the 5D world. And there have been many, many works on this. So I'm not going to say how, but very roughly all the branes, they become a node, the different kind of brane segments, and then the edges are gotten by using some tropical geometry from these brane segments. And now, okay, we have some quiver. So the key equation is that the Higgs branch of our theory, and that here, this is just some classical Higgs branch because we're at finite coupling, is going to be the 3D Coulomb branch of this magnetic quiver. And this is reminiscent of 3D mirror symmetry. And nevertheless, this is a statement that we're making in 5D. We're comparing a 5D theory to some 3D theory. There is no 3D mirror symmetry, but the Higgs branch of one is the Coulomb branch of the other. So this is, let's say, a computational tool. One can say more, but let's just view it as that. And this is a classical computation. We can see that this is true. And now what about the SCFT fixed point? Well, we can look at the brainweb corresponding to SCFT fixed point. And we can, in just using exactly the same rules, extract a magnetic quiver for this as well. Now, this is actually quite neat that the complexity or the difficulty of the computation stays the same, whether we're dealing with some super vanilla Lagrangian theory where everything is classical, or this super hard to describe 5D SCFT, which we have barely any control over. So that's actually a fantastic object because it doesn't care whether it should be easy or it should be very hard. The computation is always easy. So that's why we like magnetic quivers. And in this case, we can also see that the infinite coupling theory has now 7 moduli, Higgs moduli, and we can do the computation. We can check what this magnetic quivers gives, and it actually fits the known answer. Okay, I don't want to go too much into the details. I want to now actually address Higgsings. So now, what is a Higgsing? Well, Higgsing is moving along the Higgs branch. It's just a different name for that. So in other words, in field theory, we're giving a VEV to some field, and then we'll see what remains. So I'm not caring about any massive stuff. I just want to see what's the effective field theory at low energies. And of course, we don't have any direct field theory description for our 5D CFTs. But in our brain picture, we can take our brain web, and we can just take one of these segments, send it away, and we just see what remains. That's a Higgsing in a brain picture. And we're left with this down here, which describes free hypers. This is obvious if you know about brainwebs, and if you don't, that's fine, just believe me. Now, on the magnetic quiver side, we can give a VEV to a monopole operator. That would be now moving along the Coulomb branch of this magnetic quiver, which is the same as the Higgs branch of our 5D theory. So here I could take, for example, this node over here, and I just give a non-trivial VEV to the monopole operator, the basic monopole operator associated to that U1. And if I do that, then what remains is this theory down here. And this is a theory of free twisted hypers, so abelian vector multiplets in 3D. And so this perfectly fits. So brainweb, magnetic quiver, they're kind of the same thing. They see the same stuff. Now, I want to go to the geometry. And in geometric engineering, the same theory is described by this equation, this set of equations here, which comes from this toric diagram, which is just dual to the brainweb that we just looked at. And so this is some local Calabi-Yau3 singularity. It's a complete intersection. There are two equations, x, y is z squared, u, v is z squared. So these are kind of intersecting Kleinian singularities. And now, as I already briefly mentioned at the start, the Higgs branch is captured in geometric engineering by looking at deformations of the singularity, so opposed to resolutions which capture the Coulomb branch. Now, we can actually write down a complete set of deformations of the singularity using results from Colinucci and Vallandro. And this is what we have down here. So I'll put some parameters, alpha I, and then some monomials which capture the deformation. And if I turn all of these alphas to some generic value, I have a completely smooth Calabi-Yau threefold now. And then we're on some generic point of the Higgs branch where we're just left with some, yeah, basically nothing anymore. Okay, so now we can turn on just some single deformation. And I picked that xy equals to z squared stays the way it is, and uv equals to z squared gets an additional alpha 1x. Well, this alpha 1 is not 0. So the singularity that remains, if we analyze the singular part, is actually a so-called compound Duval singularity. And these compound Duval singularities engineer free hypermultiplets. This we can get from a paper of Colinucci, Marcos, and Giovanni and Vallandro. And so again, this fits with the side of the brainwebs and the magnetic quivers. We're left with free hypers. Everything is consistent. That's nice, is what we expect. Okay, and now we can actually take this deformation and we can map it exactly to the brain that we just moved. Why I can do this is definitely not clear from what I've said so far, but I can say this with quite some confidence. And so this alpha 1x is basically corresponds to moving this brain segment, or in other words, this alpha 1 I could interpret as the vacuum expectation value of my monopole operator in this 3D magnetic quiver. These things are all kind of the same. Now, we can also add the other deformations, everything that corresponds to moving some single brain segment. And so we have alpha 1x and an alpha 2y deformation. I should have really put the equation here again because this is not very clear. Let me briefly jump back to the equations. So we have two equations. And the one set of equations we can deform by x, y, and z. The other set of equations we can deform by u, v, and z. And over here, the x, the y, and the z are the the D5 brane moves, and the NS5 brane moves are given by U, V, and Z for the other equation. So we kind of have some mapping between these deformations, between moving brane segments, and between these monopole waves. So let's take something a little more interesting. SU3 with 6 flavors at its infinite coupling UV fixed point. I'm putting a little hat here to say that it's at infinite coupling because I don't know how to do it better. And the brane web is over here. This is the magnetic quiver. Everything looks kind of similar, just a little bit longer. That's because it went from SU2 to SU3. It's not remarkable. These things should look similar. And down here, the equation is changed only in a tiny detail. This is Z3 instead of a Z2. Now, we can look at the deformations here, and of course, it's getting a little out of hand because the dimension of the Higgs branch is just growing. And actually, we count 12 deformations, which fits the Higgs branch dimension at infinite coupling. And so what can we do with this whole mess? We don't see any structure here straight away. We would have to do some difficult computations to see what is the kind of theory, what is the kind of singularity that remains if I turn some of this on. But now I'll just kind of state how these things fit together, because I have all this technology from brainwebs and magnetic quivers. So we can look at the partial Higgsings of our theory. And partial Higgsings can be captured in what is called a Hasse diagram. Hasse diagram is just partial order as a picture. That's it. So, and nothing fancy. So partial Higgsings, of course, are partially ordered, and that's what I'll show you. So over here, we have the theory SU3 with 6 flavors at infinite coupling. And it can be Higgsed to either SU2 with 4 flavors at infinite coupling, or it can be Higgsed to SU2 with 5 flavors at infinite coupling, or inequivalently to another SU2 with 5 flavors at infinite coupling. And these all can be further Higgsed, and then we reach a trivial theory, which means just 3 hypers. And over here, we see the corresponding magnetic quivers. So down here, we have the full magnetic quiver. These are the moduli that are still at our expense. We can do some Higgsing. We have less moduli left. And what are the moduli that we should have left? Well, exactly, we should find a magnetic quiver of the theory that we just discussed. And indeed, this is what happens. And over here, we find 2 magnetic quivers. And this set of magnetic quivers are exactly those that fit inside our original magnetic quiver and that don't contain any free stuff. So we kind of know all of the theories that we can Higgs to. And now we can group our deformations of before into these different nodes in our Hasse diagram. This is all the same diagram. And we see that the deformations like x squared, xz, z squared, yz, and y squared, which kind of corresponds to d5s, they all belong to the same Higgsing, which is also seen down here. To get from down here up to here, we have to subtract the -1 from all of these 5 nodes. And actually, if I subtract the -1 from one of them by turning on some monopole VEF, what I'm left with is something that includes some free twisted hypers. I can take them away, and then I'm left with exactly this. So any one of these deformations will do to Higgs me there. And in order to completely Higgs, I can do 2 things. I can turn on a deformation that is not named here, or I can pick one of here and one of here, and this will also bring me there, because, yeah, kind of clearly. So now we've brought in some logic into these deformations. Okay, so the nodes in the Hasse diagram, they correspond to symplectic leaves in the Higgs branch. Now, if you don't know this language, that's fine, but the Higgs branch is some hyperkähler variety, and it's stratified by using the symplectic form. And the stratification matches exactly the partial Higgsing of the quantum field theory. This is quite remarkable, but also if you think about what a moduli space is, it's kind of obvious. So this is just a fact. And now we can fit these deformations into the same Hasse diagram. So we can see that using the deformations, we can probe the singularity structure of the Higgs branch. This is not the same as knowing what the Higgs branch is. We don't know how to obtain the geometry of the Higgs branch from these deformations. That's actually still a very hard problem. But we now have some path towards it. This is kind of, the goal would be to get the Higgs branch just from our deformations. But well, we don't get quite there, but we at least understand the singular structure. And so the things we did, they match were applicable with the work of Bourget, Colinucci, and Stefanamecki, and also Alexeyev, Argus, and Bousseau, just for those that know these things. And yes, I'll get to my outlook. I think it's time. So how do we obtain the full Higgs boson from geometry? Still an open question, but hopefully we can make progress. And a thing that I haven't mentioned at all, but I've mentioned at the beginning that if we are dealing with toric brainwebs and toric geometry, there's a very nice duality. So there's a kind of a one-to-one correspondence between these. And this is lost once we lose toricity. But actually, moving these brain segments and turning on these deformations and being able to match these two, we now can also match non-toric geometries and non-toric brainwebs to some extent. So this is something we want to also explore in the future, of how to deal with what is also sometimes called white dot geometries, which go beyond the regular toric diagram geometries. Okay, with that I'm done. Thank you.
Thank you. Thank you. Questions for Julius?
Hi. I had a question when you match deformations to brainweb things. The constant deformation didn't show up. What does that do?
The constant deformation?
Exactly.
Yeah, that's kind of you send everything away. Like you completely kill the singularity. Yeah. So the things that I've showed you so far is to pick a single brain, send it away. I've kind of swept under the carpet that there are other deformations which are more violent and they just send more away. And the constant one sends everything somewhere.
No, thank you.
Further questions, comments? Well, thank you again.
Thanks.
So now we're going to listen to Alexia Nix, who will tell us about NS2 Chern-Simons something. Where did it? Matter theories and precision holography. Yeah, please.
Thank you very much. And yes, special thanks to the organizers for giving me this opportunity to talk about N=2 Chern-Simons matter theories and precision holography. This is based on work that we're currently finishing up and you'll probably, hopefully, see soon on the archive together with my advisor, Frederik Goethason. So let me jump right in with a quick introduction and motivation behind all of this. As we all know, the ADS-CFT correspondence is a very powerful tool because it allows one to probe the strongly coupled dynamics on the field theory side by studying the weakly coupled dynamics on its gravitational dual by using perturbative methods. And this is exactly what we will be doing here. So a lot of work has been done in order to deepen our understanding of specifically the ADS-4 CFT3 correspondence, but this has mainly been restricted to the specific case of ABJM theory, where a lot of work has been done. Moreover, in this very nice paper by Marinho and Butrov in 2011, they found that the perturbative result for the free energy in the 1/n expansion actually resums to this Airy function, some of you might have heard of. But it turns out that more recently, people have been finding more and more evidence suggesting that this is also the case for other 3D N=2S CFTs. So specifically that the free energy on S3 in a wider class of 3D N=2 Chern-Simons matter theories also has the form of this kind of Airy function. Of course, the arguments inside it will depend on the specific theory that you consider. But this poses the natural question if this is also the case for other observables. And this is what we're interested in. And specifically, we will look at a different observable, namely the vacuum expectation value of a 1/2 BPS Wilson loop. And it turns out that for a wide class of these Chern-Simons matter theories, a lot of work has been done, but only at leading order in the large N limit. So, and the same is actually true for their holographic counterparts. So if you look at the relation that we get from holography for this observable, so we know that the holographic Wilson loop on the field theory side in the large N limit should map to the partition function of a fundamental string, if you're looking at the string theory background, or a probe M2 brane, depending if you're looking at the M theory background, right? But indeed, in the large N limit, these two things have been matched, but only at leading order. And this is true for a wide class of 3D n equals 2 Chern-Simons matter theories. But again, much more is known for ABGM theory. It turns out that in this nice paper of 2012, the authors found, they did the matrix model calculations, and they found that the 1/n expansion resums to a ratio of Airy functions. And then on the string and M theory background, there have been some very nice, also recent advances in obtaining the one loop answer. And in fact, in this nice paper here, this is actually a big motivation for the work behind this. They found the one loop partition function of the M2 brane, which also contains essentially the correction coming from the string, because you just have to do an appropriate expansion in 1/k. But the state of the art is currently that for a wider class of these 3D Chern-Simons matter theories, not much is known more than the leading order terms. So the goal of this work is to extend these existing results of the holographic Wilson loops. So on this side of the correspondence, we'll look at the M theory and string theory backgrounds beyond leading order. So we will look at one loop corrections, and we will do this for a wide class of 3D n equals 2 Chern-Simons matter theories. So I told you we're working in this large class of 3D n equals 2 Chern-Simons matter theories. But what does this consist of? It consists of two subclasses of SCFTs, which I will coin family A and family B. Family A will have a dual description in M theory. It's schematically given by this picture, and reduces to an ADS4 times the Sasaki-Einstein 7 mod ZK manifold. Now, family B is a little bit more complicated, but all you have to know is that its dual is given in massive type 2A. So it doesn't have an M theory description, so we will restrict ourselves to just getting the string theory answer on this side. And topologically, the background that you get is a warped product of ADS4 times the sine cone over the Sasaki-Einstein 5 manifold. And this is the metric that you have for people that are interested in this. But this is not super important. So because I will be focusing on the string theory side, let me just give a brief overview of the classes of SCFTs that we will consider in a very schematic way, okay? The schematic way I will use is the language of quivers, and we saw a bit of this earlier. I will do it a bit more simply, and I will just consider a very general class of G-UN gauge groups, each having a Chern-Simons level Ki, and I will denote each gauge group with a node in my quiver. Okay, so very generically, you can have this kind of necklace quiver, people call this, but this is not, like, it doesn't have to be necessarily a necklace quiver. And then it turns out that the SCFTs of family A satisfy this relation, so the sum over the Chern-Simons levels is equal to 0, vanishes, as you would expect if you have an M theory description. And for family B, the sum is non-zero. This I will denote with the small letter n, the sum over the Chern-Simons levels. As we shall see in the dual gravity picture, because you have massive type 2A, this maps to the Romance mass up to some length of the string. And of course, you can have various matter turned on, but the primary examples that I want you to have in the back of your minds are essentially for family A, ABGM, which I think most of you are very familiar with. The quiver is given by this picture. So you have a UN times UN gauge group with opposite Chern-Simons levels, so the sum is indeed 0. And then for family B, things are, again, a little bit more complicated, but the primary example I would say is an SUN gauge group with non-zero Chern-Simons level K, okay? So, because I told you I will be looking at this specific observable, the supersymmetric Wilson loop, we have already seen the definition, so I won't go into too many details, But we will consider a 1/2 BPS Wilson loop that is wrapping the equator of a 3-sphere and is given by the vacuum excitation value over the trace in the fundamental representation over the path ordered exponential of this integral. And without going into too many technical details, you can just use the tool of supersymmetric localization, and you find, which was done in a many series of papers, but it turns out that the final answer you get is given in this very kind of universal way. So it turns out that for family A, you get this very nice form, which is kind of universal, you would say, because you just have this N and K, right? N is the rank of the gauge group, K is the greatest common divisor of your Chern-Simons levels, and then you have the volume over the Sasaki-Einstein 7 manifold. The C, I will come back to in a bit, in a few slides. But then for family B, the same is actually true. So it's in the large N limit, the log of the vacuum excitation value of the Wilson loop is again given in terms of this universal formula, where N is the sum over the Chern-Simons levels. And you have now, instead of a Sasaki-Einstein 7, you have the Sasaki-Einstein 5 that we saw earlier. So let's go to the actual calculation that we did on the gravity side. The gravitational dual of family A is given by this metric in 11D supergravity. What I want you to note, what I want you to actually remember from all of this is just that the nice thing is that because you have a Sasaki-Einstein 7 manifold, you can write this locally in terms of its contact 1 form, eta, and its transverse scalar Einstein space. Of course, you have a G4 firm flux also turned on. But then, because we want to study the partition function of the M2 brane, let's see what this gives us. We have, if we do an appropriate expansion, we find that the leading order piece is just given by the classical action that you get, so the classical action of your M2 brane, right? And then the one loop partition function is the thing that you get upon quantizing your M2 brane. So this will contain information regarding the quadratic, fermionic, and bosonic operators that you will get that are acting on the fluctuations around this classical configuration of your M2 brane, okay? So in order to make this all a little bit more clear, I want you to look at this visualization. It's very schematic, but I want you to just understand this holographic picture a bit better. So we have Euclidean ADS4. The boundary of this ADS4 is, its conformal boundary is a 3-sphere. I told you that we're looking at the Wilson loop that is sitting at the equator of an S3. You can consider this to be this S1 circle. And then in the bulk, this S1 circle reduces to a minimal surface, which I call sigma 2, okay? And this would be the string picture, right? Because for the string, we just need one string that extends into the bulk and has appropriate boundary conditions such that it maps in the dual picture to your Wilson loop. But because we are looking at an M2 brane, we need one more direction, right? We have three directions that we have to consider. So 2 of these will actually be coming from this minimal surface, but the extra M-theory direction, I will call it, will be inside your seven-dimensional Sasaki-Einstein manifold. And if you consider this circle to be an S1M, it turns out that, remember, we also had this orbifold factor going on. The radius of this circle will be proportional to 1 over k, such that when you go to the large k limit, you get back a point in your internal space, right? This is the type 2a limit, so that you just reduce to this minimal surface. This is exactly the picture that you get in order to go from M theory, where you have a fixed k, to type 2a, where you just, this is a point in the internal space, and you just have this minimal surface. So, oops, sorry. Okay, so the classical solution that we find is given in terms of this sigma 2 times, so this minimal surface that we saw extending in the bulk as the string picture, times this M theory circle. Now, the nice thing is and this was done by Farquet and Sparks in 2013, that supersymmetry actually makes a very specific choice on where this M-theory circle can be identified with, which coordinates you can identify with this M-theory circle. And it turns out that it has to be parallel to the contact form eta that I told you earlier to remember, because this is coming from, let me just show you quickly, from here. But it cannot be along the Reeb vector. For people that are familiar with this, the Reeb vector is also related to your R symmetry, but you cannot choose it to be in this direction. But essentially, if you choose then, if you identify this third coordinate with your M-theory circle, and you choose this coordinate to be 2 pi periodic, what you get is that the volume of this this circle is just given by 2 pi times the radius. So the radius is indeed proportional to 1 over k, and this is where this c appears. So this c is nothing more than the radius of your M-theory circle, okay? What this means essentially is that it doesn't really matter if you have a specific kind of Sasaki-Einstein 7 manifold in mind and you have its metric explicitly, you can just read off the C from the metric. You don't even have to do a big calculation. And what one finds is indeed that you can indeed match this at the classical order. And then the fact that you have to do this appropriate calibration of the M-theory circle together with the geometric properties, the geometrical properties of your Sasaki-Einstein 7 manifold yields this very nice description of your quadratic action in terms of a 3D language. So this is actually universal. This is true for any kind of Sasaki-Einstein 7 manifold you consider, where zeta are the bosons, the bosonic fields, and theta are the fermions. So you see that they are masses. The fermions are masses in 3D language, and the bosons just have a mass m squared, which is just a constant, and it's the same constant for any Sasaki-Einstein 7 manifold. Now, inspired by this Jumbie and Seidling paper by 2023, we can use their techniques in order to reduce the problem to 2D, because we want to use known methods from string theory in order to compute, right? Because we have some quadratic operators that are acting on your fields. You want to get the functional determinant from them. You want to evaluate this. How do you do this? You can do this in 2D language. This is a well-known thing. And then in order to reduce your problem to 2D, what do? You do a Fourier expansion along your direction of your M-theory circle, which is quite natural, right? Because if you reduce over the circle, you also get back the 2D picture when your mode is 0. So you get a 2D theory with an infinite tower of fields, bosonic and fermionic, and you have to sum over them, right? You can label these modes with your Fourier modes, L, and you get a universal mass spectrum that only depends on this radius now of this M-theory circle. And then using, of course, known methods such as the heat kernel and zeta regularization, what you find is that the M2 brane partition function just evaluates to this very simple expression, the one loop piece at least. And it's universal. It just depends on the C, which you can read off from your metric. The only caveat is that this is true if this inequality is satisfied, but this is already true for large enough K. And you can apply this to various known Sasaki-Einstein 7 backgrounds, for which also the field theory has been studied, and you can find the expression in each case. And you can see already for small k, it's satisfied, which is quite nice. So let's jump to the second family. I won't go into too many details, but I just want to show you what we found there. Again, the metric is a little bit complicated. You have this warped product in front, ADS4, and topologically, this is a sine cone over the Sasaki-Einstein 5 manifold. You see here, again, you have a killer Einstein metric, you have your eta, and your dilaton is, of course, not constant, as was mentioned also in previous talks, because you have this warp factor in front, and you have this Romance mass turned on, which you can see explicitly depends on the sum over your Chern-Simons levels. Now, the string theory dual of the vacuum expectation value of the Wilson loop is just given by the partition function of the string. again, you can do an appropriate expansion. You find the classical piece at leading order, and the one loop piece is now given in exactly the same way as before. We have this kind of effective action, which just studies the fluctuation around the classical configuration, but now of the string, not the M2 brain. But you also have this extra piece, which is the Fradkin-Zeitlin action. But it turns out that for the solution that we're looking at, for the classical solution for the string that we're looking at, the minimal surface, if you want sigma 2, that we saw in the picture before, this is located at a point where the dilaton is actually constant. So then the Fradkin-Zeitlin action just reduces to the pullback of the dilaton to the worldsheet times the Euler characteristic of your worldsheet. And then indeed, if you plug everything in, you get the classical solution that was already found by Fluder and Sparks in 2015. But if you do the computation again, but on the string theory side, you find that the one loop partition function of the string, together with the Fradkin-Zeitlin action, yields this expression, which is quite remarkable, I would say, because again, okay, it doesn't look super pretty, but you again can specify everything in terms of your quiver data and the volume of the underlying Sasaki-Einstein 5 manifolds, which is quite remarkable. And this is exactly what was happening with your leading order term. Remember previously we had the log, that's why you have the exponential here. So let me conclude and give you a quick outlook. I don't know how much time I have left. Okay, perfect. So indeed, we found a universal expression for the holographic Wilson loop in both classes of the SCFTs that we studied, so both for family A and family B SCFTs. And we can apply our result to an infinite class of Sasaki-Einstein 7 or Sasaki-Einstein 5 manifolds, which is quite nice. And the nice thing, maybe even nicer thing, is that this result, the fact that you have this kind of universal answer for family A, kind of hints at a closed form expression for also the perturbative parts of your answer on the field theory side. Remember that I told you that for ABGM, people have indeed found this analytically to be a ratio of array functions. And this also suggests that, is it possible to apply also our techniques to different observables, such as the free energy? Can we find non-perturbative corrections to the free energy by studying worldsheet instant on it, etc.? And currently we're also exploring the matrix model, of course, at sub-leading order, because it's very interesting to check if this indeed matches the field theory predictions. And with this, I will close. Thank you very much.
Thank you very much. Questions? This one?
I missed. What's the meaning of C on the in family?
Yes.
Yeah. And
On the gauge theory, yes. It's kind of a tricky question because naturally you can easily say that you know that on the gauge theory side, in the large and limit, the vacuum expectation value of the Wilson loop is just the exponential times to the power of your endpoints of your eigenvalues, right, times your square root of n. So you can say that it relates to the endpoints of your eigenvalues, but not exactly, because you also have a volume of your Sasaki-Einstein 7 inside there. So it's not a direct map from this parameter to that parameter. But from the other nice thing is that you can actually map, because of course, what I didn't mention is that you have various choices for your C. You can choose you can make many different choices, right? Because as long as you're taking a valid choice that yields you a supersymmetric M2 brain, this is legal to do, but it will just map to a different field theory. Like in ABGM, for example, you have to make a specific choice to get ABGM get the dual side.
what I was wondering about is that in your answer, it looks like there is one place where C enters as a rescaling of K, and another, it's more like rescaling both of K and C and N. So it's like C is proportional to effective membrane tension plus rescaling of K. Maybe that, I don't know. Maybe that's the interpretation.
But this on the string theory side still. Yes, yes, yes. That's not, yes, yes. But on the string theory side, like on the gravity side, it's just the radius basically of your M theory circle, this third direction.
What you are saying on gauge side is not clear.
Yes, it's not very clear. Yes.
Further questions? No. So let's thank Alexia again. Very nice talk. Okay, and now it's time for Viktor Mishniakov to tell us about. I do? Well, you're not here. Could be.
The time being, I don't know.
Okay. Welcome, please. Could you come? Okay. No.
Do you hear me now? Okay.
Yes. And you will tell us about the importance of being exact, integrability, gauge, black holes, physics, and their correspondence, please.
Thank you very much indeed. Thank you very much indeed to the organizer for this wonderful conference and for this chance to me. This talk of mine will be based on many papers and works in progress with wonderful collaborators, Marco Rossi, Daniele Gregori, Ratul Mahanta, and Hong Fei Xu, and in particular with, actually two papers, one appeared today, unfortunately this is not the I didn't have time to put it here, with Marco Rossi. So this is a synopsis and also in the end motivation. So I'll be talking about quantum integrability in the form it assumes in integral and functional equations. So something quite concrete you will see in a moment, you may also know about, but trying to bring you, to lead you to a classical integrability, actually simple classical or the ordinary differential equations. In general, we would need actually a Lax pair, so some real dynamical classical system, but we will be even simpler. Why? Because actually this is the only, the ODE is somehow the only thing we need for the treatment of Cyber-Witten supersymmetric and equal to gauge theories or in the in one omega background, so Nekrasov-Shadashvili in technical words. And probably we will touch a little bit something about black holes, although I'm not absolutely an expert about it. And you can find a little bit more on papers. So I'll tackle the problem to reach, to bring you to integral equations for quantum system in a way that you already have partially seen. So what happens, I start from an integral scattering theory in 2 dimensions. So, and at the end of the day, in a nutshell, it reduces to a 2-body scattering. Why? And the 2-body scattering of this sort, in which the mass stay the same, because you have the infinite charges. Why the 2-body? Because if you go 3-body, you have the very famous Yang-Baxter equation. You have already heard about it, which tells us that the order of the scattering doesn't matter. So the n-body scattering process in miraculously factorizes into 2-body processes. Okay. Of course, I was probably a little bit too quick. You can have diagonal processes, also non-diagonal processes. So both can be really not, but you know that, not trivial. No, now it's too much. So Okay, so let's take now an example. My favorite example. I'll do something with this. So, which is Cinch Gordon. Okay, you have the coupling constant here. It plays a role in this S matrix. It's the S matrix for the only particle in the spectrum, a scalar particle, and this is the usual parameterization used in the S matrix. Okay, this is just a piece of parameterization. This is an on-shell information, as it is said, infrared, call it if you wish, an infinite size. So if you do better answers with this, as you may think of integrable systems, it doesn't work. So because we want to compute finite size things. For doing that, you need a new method you heard about, somehow thought about by Alyosha Zamolodchikov and Klassen and Nemetz at the same time, for relativistic theorists at least, in which you exchange time and space on a cylinder in such a way that you had the S matrix here on a compact space, you move it here in an infinite space, then the S matrix is a good information. The price you have to pay, of course, is that now you ended up with a compact time. But you know, thanks to Yang and Yang, that you can deal with it, promoting it to be the inverse of a temperature. So you have to introduce some thermodynamics to compute your partition function on a cylinder. You can do it leading order by minimizing the free energy obtained by the scattering matrix. And then on the right-hand side, the same free energy is, the same partition function is given by the leading order, by the ground state energy you are looking for. Let's hope it works. Yes. So equating the exponents, you get something like this, minimizing the free energy. And for relativistic models, we are stick on that at the moment. The S matrix of the mirror theory, so the other theory, is the same. So you use the same S matrix, very simple, and this is the original Zamolodchikov and Klassen and Meltzer idea. You minimize the thermodynamic function, then you do expect nonlinear thermodynamic Bethe-Ansatz equations. You take the solution and you get the energy as an outcome. In our concrete example, this is the energy. You imagine this is a sort of density, somehow valued with some thermodynamics, and this is the dispersion relation of an energy into dimension, and this is the constraint. Okay, the minimization, the outcome of the minimization. And the interesting fact, also already noticed by Roberto, I think in his talk, is that you have a trace of the scattering theory here in the kernel. Instead, there is this equation, on the other hand, recall you in the driving term that you are dealing with a massive particle traveling on a circumference of length r. Okay, and this is a relativistic particle. Now, this is exactly the same equation, written with a different, just a little different mathematical reparameterization, in such a way to make this passage from an integral equation to a functional one. But this step is not so harmless. Why? Because what I do is quite interesting, and this was really invented by Zamolodchikov. You have already this y here, you define it, and you do a sort of up and down in such a way that you cancel the driving term. And on the right, you get the bootstrap of these two kernels. This is a peculiarity of this model. Usually, you don't have a second object here. You have only one, or a product of the same theta. You may have already seen this kind of things. And already this form is very interesting. And both functional and integral equation constrain form and expansion. The expansions give you the conserved charges we start with of the solution. This is the strength and power of quantum integrability in a nutshell. So now we should try to introduce an ordinary differential equation to describe this system. I have to preface that there was already on the table a very beautiful derivation in the case of a Schrödinger equation with polynomial potential of functional equation characterizing minimal conformal field theory due to Patrick, Roberto, Marciano Lugano Zamolodchikov, and many other people among those also myself worked on. But for gauge reason, for other reason, we need here two irregular singularities. Instead, you know very well with the Schrödinger equation, with potential, you have only one irregular singularity at infinity, like in the Seiberg-Witten differential, for instance. Okay, this is an idea, and also because we want to be, we want to jump into the realm of Oin equation. Okay. Trying to do something like hypergeometric function in the Oin equation realm. Of course, we elaborated a theory, but it goes beyond of this talk. A general theory to invert somehow this arrow. This is also a work in progress partially. So to take an integral model and to get to an ODE. But this will bring us to really to a couple of lax operators, something like an itching system alla Gaiotto-Mureniesque. So it's more complicated because in general, you get the massive system. Okay. Instead, here we are somehow conformal. Okay, we will start with something more heuristic and simpler. So first of all, we notice that Y is beautiful, but actually we expect the spectral determinant to play some role, and Y to be some composite object in terms of this spectral determinant we call Q. And the heuristic idea is that we know already a functional equation in quantum mechanics. We know the unitary condition between the reflection and the transmission coefficient. This can be read off as a sort of, say, functional equation. Okay, let's try to be effective, and Seiberg-Witten theory can be of some help here. Why? Because the original Seiberg-Witten idea, made very, how to say, simple, very simple, is that to take, consider here not, this is already a quantization, consider here the momentum, so really the classical Seiberg-Witten original idea. So you have a differential. Their idea was using a suitable differential, and you make the integration around a cycle, and you get the electric period. Then you invert this relation. U is the energy, if you wish, but also in gauge theory is the trace of the square of the field, or the Coulomb branch modulus, and you put the U in terms of A in the dual period AD, the same integral, the integral of the same differential, but on the other cycle. And in this way, Seiberg-Witten tells you that this is the differential of the prepotential with respect to A. So you get, in the end, the prepotential. The same, at least in principle, can be done using the quantization with omega background, only one, epsilon 1, and you have to start with, instead of a differential, with an ordinary differential equation, a Schrödinger-like equation like this. In this case, for pure theory, SU2 theory, this is exactly the Mathieu equation, which is periodic, and the solution, as well known, satisfies this interesting Floquet movement with this phase. But let's focus on functional equation. Let's try to derive functional equation basically for this equation, which means for the periods. First of all, we have to recast a little bit the equation in such a way that is more suitable for integrability, okay, and just changing the potential to be a confining potential, and getting a map from gauge on this side. You have here the omega background deformation, the instant uncoupling. This is the rapidity in integrability world, and this is Coulomb. Okay, so can we use this to be compared with quantum Saint-Gordon? Not directly. You have to introduce at least in a suitable way, using some B over B goes into 1 over B symmetry. You have to introduce the coupling constant. You make it more complicated, and then you can analyze this equation because you have made effective these two symmetries. The ingredient of this theory is to have discrete symmetries I've already shown you, which are broken by these fundamental solutions. These are the solutions going to 0 uniquely, to 0 at minus infinity and plus infinity. Of course, if you act with ones with the symmetries, you go from U0 to U1. U1 is the exploding one, and similar for V1. Okay, and in this way you get also rigorously the exploding solutions. Now, of course, you define the Wronskian of these two solutions, and this is the spectral determinant. And thanks to the way in which we define the symmetries, the equation at this symmetry, you have, thanks to this definition, you have this. This is the link between the U basis and the V basis, okay? And these are the connection coefficients. The lambda symmetry gives you this translation, and then if you act on this equation with the omega symmetry, you get the second one. And this is the change of basis. So, in other terms, this is Q is the connection coefficients. Then you can construct also more complicated connection coefficients. People working on exact WKB, research, they know this very well, which actually are Roskian in different anti-Stokes sectors. But I don't want to be so complicated, although we need D, we will see in a moment, but anyhow, you can do it. Then, as promised, we do the final step. We take, as in the course of quantum mechanics, the Roskian of the left-hand side and the Roskian on the right-hand side. We get the QQ system, okay? And this will be, in the SFT, might be called also quantum spectral curve under many respects, okay? Now, the return of the Y system. Why? As said, the Y system is a composite object. You have to multiply it to Q, it's quadratic, and then you get exactly the same Y system before from the QQ system. So it seems that actually we have got a differential equation fully equivalent to a field theory. The point is that the Y system is the same. The solution is the same. This is a delicate question. I don't take time. And the answer is not, because there is this tricky point here in the inversion of the right-hand side of the Y system. So the path cannot be inverted, but still is you can check carefully. It's the massless limit of Sinch-Gordon theory. So it's Liouville field theory. Is this, you see, there is only one exponential, not two, which is good. This is what I promised. So we get only conformal field theories with only one ordinary differential equation. And actually, we see the gauge theory only at the so-called self-dual point, B equal 1, okay? And this is the map. Only at this point you have also the gauge theory interpretation. For this point, we found this beautiful interpretation of the transfer matrix in integrability in terms of the electric period and the Q function, okay, in terms of the dual gauge period, the monopole. Now, if we elaborate a little bit, this is the original Q system in integrability variable, in gauge variables, we get this. We invert now this, and now the TBA equations are twofold. There are two pseudo-energies, U and minus U. And this gives us already the spectra, the spectra of Seiberg-Witten theories at strong coupling. This is the monopole, and this is the dione. But actually, going from there to weak coupling, so to recover A, the electric path, is a complicated fact. People know that there is wall crossing and so on and so forth, but integrability gives you a sort of shortcut. There is another relation, the TQ system, and which is a sort of fusion between the weak coupling and the strong coupling. Now, the conserved charges are in the expansion of these quantities when theta goes to plus infinity. You get, this is the usual story in integral theories. And also, elaborating a little bit, in this way, you find the so-called quantum periods. At zero order, you get Seiberg-Witten and then the quantum correction. But now we want to focus on the other regime, which is the one in which you have the instanton expansion, which is instead not asymptotic but converging, okay? When lambda, instant coupling, goes to zero. This is the Nekrasov-Vokunkov expansion. So where is the prepotential in this picture? Is inside the connection coefficient. If you write the connection coefficient in this form, which seems a little magical, but I'll show you why, AD appears here. And from AD, you have already the prepotential thanks to Seiberg-Witten geometry, to this relation. How do you discover this? You use this as one way is you use this as an answer. The QQ system played in the functional equation for the dual period, and you can solve it. And you show that the, say, prepotential by Nekrasov and Shadashvili give you the unique solution of this equation. Another more instructive way is to look at new objects here. I'm introducing now the ODE-EN, instanton correspondence, the Floquet basis. The Floquet basis is new in the integrability world somehow. You have that in the Floquet transform in this way under a period, okay, you can ask what happens if I go the same but from minus infinity to plus infinity. It acquires similarly a phase. This phase, you can prove thanks to this functional equation, some tricks, is exactly the dual period. So it's the phase acquired transversally by the same Floquet function. So we have discovered where somehow the prepotential lives in this picture more directly. And so this means that we have an expression for phi, and we can make many computations. This is not so easy. At least it's more complicated than computing the Floquet, because the Floquet is an integral, as you well know, over the quantum momentum on a compact interval. So y is finite. Here for me now, instead goes to, apart from the regulators I have to put because these are exploding objects. But anyhow, I have to go from minus infinity to plus infinity. So it is not so obvious to make this kind of calculation. In fact, we use a method which is somehow is a reminiscence of what, so it can be called kink method, but and it's quite, so I have no time to go into details. But we learned an important lesson from gauge theory. We learned that it's better to compute phases, to compute the exponentials, so the quantum momentum instead of the wave function. And this quantum momentum actually is given in terms of a convergence series of this kind, okay? And there are two kink intervals. This is a little bit technical. I can't go into details. And actually, there is, thanks to AGT, there is AGT correspondence. There is the fact that, and we checked that, people discovered that the wave function, at least they should be quivered by some quiver, and we checked that. The quiver gauge function is an extension. The partition function is an extension of the gauge theory we started from, because it's a quiver. Now we implement the idea to go using this extra phase from the Floquet basis to the decaying phase, from the Floquet basis to the decaying basis. And of course, this is done by calibrating in such a way that the Floquet which are exploding they cancel the divergency, and you get this change on basis, making the Wronskian of this side and the other side. You get the relation at the beginning. Actually, this is more general. This holds for any Euler equation, okay? If you use, you can compute this in the specific case of Mathieu equation, and you exactly obtain the result I promised, but you can do it more generally for any Euler equation, okay? And we also have all the ingredients computed, 3 ingredients, 1, 2, 3, to write down these two functions. And there is also a better understanding of what people call the Floquet approximation, in which you see U0 is directly given by this Floquet discharging fully this other piece, because this is a non-perturbative correction of this kind. It depends on why you cannot be too close to the so-called horizon. Okay, this is just how much time do you have? Okay, so this is a little bit of say very briefly what happens for when we try to use these things, but very oversimplified thing, when we try to use this thing for black holes, say that in general, so we will talk about a little bit about Schwarzschild and Kerr, and this is again for Schwarzschild. So you have, if you perturb your Schwarzschild metric with a scalar electromagnetic field or the graviton, you get a partial differential equation. So these people discovered that this partial differential equation at first order, there are many subtleties, anyhow, can be separated into radial and angular part. So, and for instance, if you do this with a sort of simplified model, although many people, Gubser and collaborator, but also Massimo Bianchi and collaborator worked on this model, which is more a sort of brain, black brain instead of black hole, and you have this equation, which is the radial part of the Regge-Wheeler, if you wish, in the Schwarzschild, the analogous of the Regge-Wheeler in the Schwarzschild case. And if you do this map, you end up with this equation. They knew already this. means. The crucial point we observed is that the function we use in integrability are exactly the ingoing function at the horizon and the outgoing at infinity. So are exactly those functions. Now, if you add flavors in to the gauge theories, you go to more realistic black holes metrics. For those, we have also new Y systems and TBA equations. In particular, in the recent time, we focused on NF equal 4, and then we made the confluence to NF equal 3. This is the number of flavors you add in the gauge theory, in which you have exactly this equation. And for this equation, we are really able to tackle the problem of the Tukowski equation for Schwarzschild and Kerr or Regge Wheeler. And of course, there are people that instead of using integrability, I have to mention this, that there are many, are using gauge instantaneous calculations to tackle these black holes computations using the partition function. But often they have to have information about the wave function, they have to enlarge the gauge theory to be a quiver gauge theory, so with a more complicated, say, gauge group. So, quasi-normal modes in a slide. So you may have already understood that quasi-normal modes arises when you impose your solution, the boundary conditions to be like V0, but also U0. So you are imposing this to be 0. But this is exactly the same condition with which we define beta roots. So quasi-normal modes in this picture, although complex, are nothing but the beta roots of the quantum integrable model. And this is a slide which tells you that this is the only TBA for the integrability, gives you the spectral determinant, and the spectral determinant enters in the end the waveform, so the solution of the partial differential equation. And maybe this could be of interest for calculations also in gravitational physics beyond and not only in gauge theories. There are some conclusions and perspectives. So I think I leave time for questions if there are, and I would like really to thank you.
Thank you. So, are there any questions or comments for David?
There is one over there, I think.
Hi, thank you for the talk. I just wanted to ask, I mean, the thing that you started with, I mean, is sort of well known to correspond via, say, Nekrasov, Rosli, and Shatashvili to semi-classical Liouville, because you're in this Nekrasov-Shatashvili limit somehow. Yet now you get this self-dual Liouville instead. Can you say something about this?
Absolutely. So yes, very good question. It seems so. Yeah, this is not the IGT correspondence. What you mentioned, that the semi-classical Liouville, C going to plus infinity, just to be even more explicit, since I like to be explicit, is true in the IGT correspondence, no? Like instead the self-dual is C equal 1. Is the other. We have also information about self-dual. I don't have time because we have the blow-up equations. Our reveal is a little bit mysterious because actually I have a question for you. What is our Liouville for bit different from 1 doesn't have any correspondence in gauge theory. So it's somehow orthogonal to the IGT1. It would be beautiful, although it's not true, that B is the other omega background, epsilon 2, but it is not the case. It's too simple because you know that you have a partial differential equation, Belavin Polyakov-Zamolodchikov, basically, for the general backgrounds. So it's another Liouville, and it will be interesting to understand how can be interpreted fully in terms of gauge theory. We don't have this interpretation. Only one point, which is special, deserves of this calculation. And actually, there are, of course, instead, the integrability theory is valid for any B. But what is missing in the integrability theory, to be honest, is the prepotential. So the prepotential solves somehow what is technically called direct and inverse monodromy problem. Instead, for B different from 1, you don't have the prepotential. Or better, we should work on this to find the prepotential. The formation of the Nekrasov-Shadashvili prepotential. I don't know. Also, the instanton expansion will be delicate.
Okay, any further questions? If not, let's thank David once.
Thank you.
And we have a 5 minutes break now.
Okay, great. Survived the last lecture. We're super happy to have Oliver Schlotterer, and he will tell us about integration on higher genus Riemann surfaces and string amplitude.
Okay. Thanks a lot for the kind introduction. So in this talk, I want to present the math problem of performing integrals on higher genus Riemann surfaces. And I want to argue that this math problem is in a fruitful symbiosis with string scattering amplitudes. So this is material drawn from joint papers with mathematicians, Benjamin Enriquez and Federico Zerbini, and with physicists, Eric Doker and Martin Hilling. But apart from thanking my collaborators, I would like to send most of my thanks to those people who made it possible that we are meeting here this week. So, as the last speaker of the conference, it's my particular honor to send a big, big thank you to all the organizers. Please join me for the applause. And we should particularly thank Magdalena, who dedicated the largest chunk of energy and time to all of this. Good that you're close enough for a high five. Fantastic job, Magdalena. And there are many other dear colleagues who are not working full-time as scientists, who are absolutely essential for the success of this event here. So also big thanks to Jimmy, Olga, Anastasios, Elvira, Hans, and possibly people that I forgot. Okay, I understand that this is the last talk between the end of the conference and you. So let me try my very best to be gentle. I think I should dedicate at least half of the talk to motivation and context. So once more, we want to integrate on higher genus Riemann surfaces, and I owe you some explanation why. And then in the more technical part of the talk, I will introduce the specific protagonists who do integrations for you, namely polylogarithm functions on these Riemann surfaces. And I will try to make some connections with string scattering amplitudes. So the motivation for this talk, for me personally, it begins in the high school days. When we learned about calculus, our math teacher told us that doing integrals is much harder than to do differentials. And as a teenager, I found this pretty frustrating. Well, I still find it frustrating nowadays. So the goal of the talk is to mitigate this a little bit. So here's an example for this kind of inequality. Take a rational function, r of x. Taking its derivative will surely be rational, no doubt. But if you take an integral of a rational function, even in an innocent example like 1 over x, then all of a sudden you're out of the realm of rational functions and you get some more funky things like a log. But adjoining the log alone is not enough to complete the rational functions under doing integrals, because if you integrate the log further, maybe with more rational stuff, then you get yet another new function known as Li2. So clearly this is a never-ending story. If you want to complete the rational functions to close under integration, then you need more and more special functions that generalize the log in Li2. And even though that function space is infinite in size, there are still good organizing principles to work with it quite efficiently. So the completion for the rational functions are known as multiple polylogarithms, and they are here defined recursively. Start with the trivial polylog, where you have an empty set left of the semicolon. This is 1. And whenever you want to add variables that are tracked on the left of the semicolon, you do an integral, essentially against a simple pole or a d log. And here the integrand is a shorter MPL. So this is really a recursion in the number of entries here. And clearly, some of the functions you know and love are part of this family. To introduce a little bit of jargon, I will repeatedly speak of integration kernels for various geometries, including higher genus Riemann surfaces. And whenever I say kernel, I mean these things whose iterated integrals you take. Okay, the geometry for the content of the previous slide is the Riemann sphere. Because what we did is we take rational functions that naturally live on the Riemann sphere and we completed them to be closed under integration. And I should add, these polylogs are the smallest function space to do you the favor of closing. I mean, we want to work with a function space that is controllable. We don't have any kernels with a double pole, triple pole, quadruple pole, simply because we don't need them. You can use IBP, integration by parts, and make sure that at the end of the day, you get away with rational functions and these polylogs, which are iterated integrals over simple poles, as opposed to higher order ones. And they close not only under integration in Z, which is somewhat obvious from the definition, but they even close if you integrate in these P variables here. This is a little bit harder to see, and in one way or another, you need partial fraction to make that happen. If time allows, I tell you about higher genus version of this partial fraction relation. Yes, please. Oh, sure, there can be divergences for all kinds of choices. And don't worry, there is a well-understood regularization prescription. Whenever some of these integrals diverge at the endpoints, there are ways to nevertheless work with them and have algebraic properties like shuffle relations go through, also in the divergent cases, which can be regularized like such. Okay, so these polylogs are the way to deal with integrals on the Riemann sphere. But what if you plan to integrate on a more complicated geometry? So let's make sure that complication grows in a bounded way. After the sphere, as string theorists, we want to next look at the torus and see what happens if we attempt to do integrals there. So here on the torus, the name of the game is to integrate rational functions in two variables, x and y, subject to this polynomial equations here. That's the hyperelliptic representation of the torus. And one way of proceeding is to change your alphabet of integration kernels. No longer the dx over x minus p only, but also you need square roots. I mean, all these y's downstairs, they are, if you solve this equation, a square root of a degree 3 polynomial. So taking iterated integrals of those kernels here gives rise to the space of so-called elliptic multiple polylogarithms, again designed in a way that they close under integration. And there are many, many ways of spanning elliptic polylogs, and here's just a small sample of possible references where you can read more about them, written jointly by mathematicians and physicists. Okay, after the torus comes, at least to my taste, the higher genus Riemann surface. So this will be the main objective of this talk, to give you means of doing iterated integrals on a higher genus Riemann surface. Let's take the genus to be arbitrary H. And perhaps it was a little bit misleading to point out hyperelliptic representations, because such a polynomial equation only covers a subset of the moduli space of higher genus Riemann surfaces. But the results you're going to see, the results won't involve these polynomial equations and will be valid throughout moduli space. Also the non-hyperelliptic surfaces that arise starting from genus 3. But a big word of modesty, this talk is not attempting to deal with higher dimensional varieties. I mean, by sticking to Riemann surfaces, we only deal with geometries whose complex dimension is 1. But ideally, we would like to deal with integrals also on higher dimensional varieties, such as K3, Calabi-Yau, and more, and that is left to the future. So the exercise of getting integrals under control on Riemann surfaces is, if you wish, a temporary step in the bigger research agenda of doing integrals on arbitrary geometries. Good, this was the computational prelude. It's time that we talk about physics. So the overall slogan is that scattering amplitudes are a context where your integration skills are converted into physics insights. One example being the Feynman integrals that are ubiquitous in quantum field theory scattering amplitudes and also in those of perturbative gravity. And here are a couple of scenarios where it's important to be able to integrate on non-standard geometries. For instance, for certain standard model interactions, such as TT bar production or Möller scattering of electrons, you should be able to deal with Riemann surfaces of genus 2 and higher. So there are specific two-loop processes experimentally relevant, where the answer is, in one way or another, a genus 2 polylogarithm function. And as a motivation for the higher dimensional geometries, sadly not covered in this talk, I was surprised that the amplitudes community produces publications in Nature. So this was about gravitational precision computations. I think the 5th post-Minkowskian order for certain non-conservative black hole observables. And there you find Calabi-Yau geometries in the multi-loop Feynman integrals. Now, apart from QFT, there is another physical theory we like very much, where integration on higher genus Riemann surfaces matter, and I will zoom more onto that. But I also speculate for myself that being able to integrate on Riemann surfaces, it should be pretty universally applicable. So maybe sooner or later we hear from other fields outside high energy physics where people might be happy using such polylogarithm functions. Okay, so some string theory motivation for this talk. String amplitudes in the perturbative sense are naturally arranged in terms of Riemann surfaces with marked points for the external states. You're supposed to integrate over the full moduli space of these punctured surfaces. So for each external state, there's a marked point to be integrated over. And there are many reasons to know about polylogarithms if you want to get information out of these moduli space integrals. So for instance, if we go for tree level, the sphere with marked points on it, then these integrals can be evaluated order by order in alpha prime in terms of so-called multiple zeta values. These are polylogs at special points, z equal 1 if you wish. And even if the answer is just numbers, namely multi-zetas, it's really valuable to know that intermediate steps, when you integrate one puncture after the other, you have some polylogarithms in the intermediate steps. So this information, for instance, reveals that closed strings are single-valued open strings. This is a certain number theoretic rule, how the multi-zetas in an open string calculation is projected to those multi-zetas that survive in the closed string result. And this is a well-established story in flat space-time, but recently these ideas evolving around single-valued multi-zetas have propagated to ADS. Really impressive literature over the last years, many authors. And it's great that we saw a poster from Aurélie about that. And here I'm highlighting two recent papers on that subject of string tree-level amplitudes in ADS, where tremendous progress was made. Yeah, also the author here, Konstantin Bauner, is in the audience. Okay, so this is a tree-level incarnation, how polylogs help you alpha prime expand string amplitudes. And similar statements go through for genus 1. So for instance, if you want to know the effective actions and loop-level contributions to them, perhaps as a practitioner of S-duality, then it's really good to have elliptic polylogarithms in your toolbox. And yeah, techniques derived from elliptic polylogs were essential to harness the so-called modular graph forms that are, if you wish, the key steps towards getting r to the 4 and d to the n r to the 4th interaction out of that diagram. Yeah, there was also a poster by Johan Sohnle on this circle of ideas. Good. As I just said, polylogs are useful to integrate over the marked points, but slightly paradoxically, polylogs are even good to learn about the integrand, even if you haven't started to integrate yet. I mean, these innocent-looking diagrams, they represent conformal field theory correlators of all the vertex operators, which insert the physical states on these world sheets. And for superstrings, the correlation functions starting from genus 2 become fiendishly hard, at least if you want to have them in a form that is amenable to low energy expansion. And I believe that the integration kernels that you will see today will be essential to run bootstrap programs to determine the correlation functions for multi-particle cases and multi-loop amplitudes from some general properties and consistency checks. So in that sense, the techniques evolving around polylogs are useful for both the integrand and the integrals within string scattering amplitudes. Yeah, and as you can see from these two examples at bullet points, there is in general a really good symbiosis between concrete questions arising in string amplitudology and some mathematical developments somewhere in between number theory and algebraic geometry. This brings me to the end of the more motivational part with a general context. And now I will proceed to a slightly more concrete discussion of higher genus polylogs. It's a good time to ask a question if you have something urgent on your lips. Okay, then let's go into the hands-on part. Notation for Riemann surfaces of genus H is this sigma. Here's a cartoon in the genus 2 case. And the one-form cohomology will always have a couple of abelian differentials. These are holomorphic one-forms. It's a total of H of them if you are a genus H. You can pick some normalization conventions using the A cycle periods, but then you can't control the B cycle periods. So it's these capital omegas, the period matrix entries, which represent the complex structure moduli of the surface. And in the context of integration kernels, these abelian differentials, they are a must. They will be among our integration kernels. But as you can expect from genus 0, for the first polylogs you saw, they came from integrating simple poles. We also want to do that at higher genus, so there must be some singular kernel besides the abelian ones, which are holomorphic. But the omegas and simple poles themselves are not enough. I will argue that you will need many more kernels to really ensure that the polylog function space closes under integration, which was the initial selling point, what these function spaces should do for us. And whatever comes beyond, the packaging device for the rest of the talk is a flat connection. Let's package the integration kernels here and those and whatever else it takes into a big connection J, valued in some Lie algebra, and as a starting point to construct good spaces of iterated integrals, we should make sure that this connection obeys the Maurer-Cartan equation. So here, flatness condition. Okay, so handing you a flat connection is more or less as good as telling you how the polylogs are constructed. Now, what kind of properties would we want to see from our integration kernels and their flat connection? Well, a natural wish list after having seen the genus 0 case is meromorphicity would be great. Single valuedness would be great. I mean, dx over x minus p is single valued. And at most simple poles would be great. But these properties don't go well together starting from genus 1. For instance, you probably know that story about the Weierstrass P function. It has a double pole. It's elliptic, but it doesn't have an elliptic friend with just a simple pole. So that's the counterexample already at genus 1, that you can't have these three pleasant properties at the same time. And I'm personally, well, emotionally quite attached to the third property. I will only present connections that obey the simple pole criterion. And then there are two options. Whom do I sacrifice? I will give you a non-meromorphic connection, which has single-valued kernels. And independent on that, I will give you a meromorphic connection, where we sacrifice the single-valuedness with respect to the homology cycles of the surface. And either way is fine. In the end, you span the same function space of polylogs, no matter if you follow the single-valued route or the meromorphic one. Okay, so these were the generalities, and I will now go for the single-valued connection. Just with simple poles, but no meromorphicity, unfortunately. And the central Lego brick to derive the entire flat connection is the two-point function of the free boson on the genus G surface. So all of you who have experience with worldsheet calculations will recognize the logarithm here. On the sphere, the two-point function of the free boson is just the log and nothing else. But once you are on a torus or a higher genus surface, you need to add something to make that single-valued. Single-valued under moving the points around the homology A and B cycles. I don't think I want to show you the explicit construction here, how to do this plus single-valued completion, but it's a pretty well understood process involving theta functions, prime forms, and more. And in fact, we can completely bypass the details of the single-valued completion. You can characterize this Green's function by three properties. Namely, being symmetric in the 2 points, having a nice Laplace equation that reflects the log behavior, and integrating to 0 against a specific volume form kappa. By the way, I will use Einstein summation conventions here and there, and whenever you see upper indices, I'm cheating in some inverse of the imaginary part of the period matrix, just as a small confession about the notation in use. Okay, so summary of that slide, there exists a well-understood Green's function on 2 copies of the surface, and that one I will now use to construct the flat connection for higher genus polylogs. I promised simple poles, and an easy way of getting simple poles is to differentiate the log. So here the Green's function representing the single-valued flavor of the log. So this is probably the term you expected, but you need a few more kernels to make sure that the polylogs close under integration. So this is not yet visible from the material here. Just trust me that you need an entire matrix worth of integration kernels that accompany this simple pole here. So it's a matrix with indices I and j, both of which run from 1, 2, ... all the way to the genus of the surface. So for those who work a lot on the torus, then you won't recognize the first term, because this term trivializes on the torus, because as a 2 tensor, this is traceless. Okay, so we start with a matrix worth of integration kernels that contain the simple poles. And now on top of that, for closure under integration, we need even more integration kernels. And everything higher, we generate recursively by doing convolutions. Has a similar flavor as the iterated integrals we will eventually do, but notice that here is a surface integral over the Riemann surface. So these f's are 1,0 forms in the integration variable z. So we need to get a 0,1 form here to make this a volume form, to make this something that we can meaningfully integrate over the surface. And as you know from convolutions, they tend to make things less singular. So while the 2 index f has a simple pole, all the f's with more than 2 indices are completely regular throughout the surface or throughout the 2 copies of the surface where the points x and y can live. So Fij is the only case with singularities. And yeah, as I promised, they're not going to be meromorphic. So here is a kind of recursion under doing anti-holomorphic derivatives in the point x. Good. Let's now assemble the connection. The previous slide provided for you an infinite tower of tensors denoted by f with more and more indices I upstairs, all of which run from 1 to 2 ... to the genus H of the surface. And we are now decorating them with certain non-commuting bookkeeping variables. There is an A variable, and there are B variables, both here and there, entering through adjoint actions. So everything in red here, these are non-commuting variables. In mathematical terms, they are generators of a free Lie algebra. So you just need to know all the words in A's and B's are independent. No relations whatsoever. So good news, you can then, by taking coefficients of these words, extract all the tensor components that you may want to look at. Okay, so I confess that the Fs are not meromorphic, but this is a feature rather than a bug. By this property of the F tensors, one can show that the connection here is flat, that it satisfies the Maurer-Cartan equation. This in turn means that you can put it into path-ordered exponential. You look at the solution to the differential equation, d of that is the flat connection times the same pxp. So this is defined as a series of iterated integrals. Here we integrate the connection once. Here is a double integral, and I leave it to your imagination how it goes on. So this is completely explicit since you know what the connection is. And since the connection expands in A and B letters, the entire pxp can be expanded in the alphabets of A's and B's. So now we define higher genus polylogs gamma as the coefficients of that pxp when you extract a particular word in the A's and B's. So here's an example along with a two-letter word, and typically you mix integrals with different numbers of iterations, coming from the fact that flatness arises from both the dj and the j wedge j term. So connoisseurs of the Brown-Levin elliptic polylogs from genus 1 will recognize this object here. Okay, concerning the modular properties. Well, the moduli space integrand for higher genus string amplitudes enjoys an invariance under the modular group SP2H, Z. So here, this amounts to changing the basis of homology cycles such that the intersection pairing is preserved. Under these modular transformations, the Green's function is invariant. Remember, the Green's function was the central Lego brick to construct everything else by derivative and convolution. And correspondingly, the Fs are modular tensors in the sense that if we do an SP2HZ transformation with this block form, then all the indices get matrix multiplied with these automorphy factors C omega plus D. So at genus 1, these are the famous C tau plus D factors. And there's also an inverse for the lower index. So the integration kernels have excellent modular properties, and the entire flat connection is modular invariant if you prescribe A and B to transform. So the good news is that not only the Fs, but even the polylogs generated from the Fs are modular tensors. So you can really control how they behave under modular transformations. Now I'm wondering, Pavel, what's the timing? Okay, good. Then I should be quick in presenting you the alternative. So if you are a more meromorphic person and don't insist on using single-valued kernels, here is an alternative to span the same space of polylogs. And that alternative was already in the math literature from 14 years ago by our collaborator Benjamin Enriquez. He showed the existence of a flat connection with pleasant properties. He indirectly defined functions G, which have the same enumeration like the Fs, but which are meromorphic and have good monodromies in the sense that moving a point around the A cycle is trivial, and moving a point around the B cycle is somewhat covariant in the sense that the right-hand side, all the B monodromies, are expressible in terms of the same family of kernels G. Okay, this math paper is really seminal, but sadly it didn't give us an explicit construction. So clearly the physicists were pretty hungry in getting something hands-on, an explicit version of these Gs. And the first group to succeed is the Zurich group, represented by Konstantin in the audience. So they constructed the G kernels using Poincaré series, I think for hyperelliptic locus on the moduli space. Then a second construction of these Gs takes a detour through the Fs. So I told you about this flat connection to generate the polylogs. And if you do a gauge transformation of that, you eventually get to the generating function of the Enriquez kernels, the meromorphic ones. So the details are a bit nifty, that you need to do a Lie algebra automorphism along the way, but it can still be worked out order by order without any obstructions. So this is second explicit construction. And for timing reasons, I won't show you the details of a third explicit construction, but let me just say that the G kernels, the meromorphic ones, can be obtained from the prime form and certain acycle convolutions thereof. Okay, so there are these meromorphic friends G that have similar properties to the F tensors from before, and which we can use to construct higher genus polylogs. And we don't have to worry about homotopy invariance. We don't need to extract words in A's and B's of a bigger object. We can just do iterated integrals of the G kernels as they are. So there's a bit of multi-index notation that you need to make this pretty. But yeah, so let's say these are the meromorphic formulations of the higher genus polylogs. And as I said, equivalent to the construction from the F tensors that you saw before. Good. This is a strings conference. So let me again connect with the concrete tasks in string amplitudes. As I emphasized before, this Green's function here, which was at the beginning of constructing the F tensors, this is a two-point function in the conformal field theory of the free boson. It, for instance, enters the ubiquitous Kober-Nielsen factor, which you will always meet in genus G endpoint amplitudes. No matter how complicated the supersymmetry details of RNS or pure spinors are, you will always have this Kober-Nielsen factor. So this Green's function is all over the place. Now, if you do superstrings, say in the RNS formulation, there's also a worldsheet fermion that you have to wrestle with. So what kind of gadgets do you get from the correlators of the fermion? And this is a natural arena to get either the F tensors, built from surface integrals of the Green's function, or from the Enriquez kernels, obtained from A convolutions of the prime form. You have the choice whether you prefer using the F's or the G's. Both of them are natural languages to take care of these fermionic correlators, namely to capture all the dependence on the marked points here. So for that reason, since the F tensors and G kernels appear naturally from fermion correlators, for that reason, we expect that everything else in the integrand for string amplitudes is expressible in that language. And there are also some selection principles up to how many indices you need to go once you fix the genus, once you fix the multiplicity. Okay, I think in practice, I should be careful about things that go beyond genus 3. I mean, I don't want to question the non-splitness result of Donagi-Witten, but the concrete construction sites that we have on our bucket list for the next 2 or 5 years is to try our luck at genus 2 and 3 at the endpoint level, how we can do bootstrap programs based on these F and G kernels. But yeah, originally, these kernels F and G are designed to do integrals for us. So clearly, they will be pretty useful to do the integrals over the marked points here in an alpha prime expansion. Sorry, I forgot to put an alpha prime into the exponent. Each order in alpha prime will have an extra function of a factor of Green's function that you should be integrating. But so far, this setting of polylogs is not yet there to integrate over the complex structure moduli. So fortunately, we saw in the talk of Lorenz Eberhard that there are really, really beautiful methods under development to deal with integrals over tau. So I believe this program of the authors here, it is perfectly suited to be generalized to higher genus, and that's something really important. Good. Then in the leftover time, I will talk a little bit about the closure under integration. So this was the selling point I made at the beginning. Why polylogs? Their raison d'etre is that they should give us a function space that closes under integration over points. And I want to at least indicate why these F and G kernels do the job. So here's again the recursive definition of higher genus polylogs in the meromorphic formulation. And it's pretty obvious that they close under integration over Z if you only look at products of such a gamma twiddle and a G. So a lot of primitives in Z come for free by definition. But let's now look at the less obvious parts. Maybe you want to take a product of gamma twiddle with such a kernel, which is a one form in P, and then ask for integration over P rather than Z. So these delicate cases, when you don't do the obvious integrals, they require some functional identities of these kernels. So here's one example. What if you integrate a gamma twiddle not only over a abelian differential, but also over a meromorphic kernel that depends on Z? This doesn't fit to our definition yet, but it starts fitting the definition once you use this interchange lemma here. So the left-hand side is nasty because Z appears in two factors. But the right-hand side is much more friendly for integration over Z because only one of the factors depends on Z. And you can use the definition of gamma twiddle. So this was just a warm-up example how kernel identities are essential to implement the closure of the polylogs under integration and really to derive practical algorithms. So here's another example of such a functional identity, and they are more complicated identities, which also have free indices I and K here, and involving 3 points. So this is what I advertised at the beginning as a higher genus incarnation of partial fraction. So at genus 1, they are literally the Fay trisecond identity, and in view of the parallel with the genus 1 case, the identities like here are sometimes referred to as Fay identities. And in fact, it doesn't matter whether you work with the single-valued F kernels or the meromorphic G kernels. These functional identities on the slide are all identical. So as you just saw, I renamed G into F, and all the identities are still true. Hence, the integration algorithms I advertised will take an almost identical form, no matter whether you use the G's or the F kernels. And here is the showing off slide, just to convince you that this can be done for an arbitrary number of indices. Maybe you need combinatorial tools like a shuffle product, but this can also be done, this can all be done nicely and recursively. And yeah, the proof for this equivalence FG was also done by the Zurich group. So please don't let Konstantin escape. Chat with him after this talk. Good, so these are the mechanisms that make sure that the polylog spaces close under integration as promised. Good, time to wrap up. I gave you 2 constructions of polylogarithms on higher genus Riemann surfaces. You can choose between single-valuedness or meromorphicity, or you work with integration kernels that have higher poles. I haven't been brave enough so far. And the connection to string theory comes about from the Arakelov-Green's function, namely the 2-point function of the free boson, which is all over the place in scattering amplitudes of arbitrary perturbative string theories. So we constructed these F tensors, which were the integration kernels. They arise really natural in the worldsheet CFT. In particular, the worldsheet fermions of the RNS superstring, their correlators are particularly natural to be expressed in terms of the F tensors that don't simplify to Arakelov-Green's functions themselves. And for alpha prime expansions, yeah, we are in a good position now. We can, in many cases, use the definition of polylogs or use integration algorithms based on Fay identities. And for closed string alpha prime expansions, we will also need to look at single-valued versions of these higher genus polylogarithms. Yeah, so there's a lot to do. I hope I gave you a glimpse of what has been done and what will keep us up at night for the next years. Thanks a lot.
Thank you so much for this beautiful talk. And we have time for questions.
Yes, thank you for the talk. And so h equals 0 case, the simplest example, beyond the rational case is the log dx over x, and h equals 1, you put the square root of a cubic polynomial. And just the simplest example, h equals 2, what you put there, without listing so many indices, just one example.
Okay, yeah. So disclaimer number 1, all the formulas in the second part don't apply to h equals 0. Don't try to recover the sphere case from them. Then if you specialize this formula to h equal 1, then clearly you won't get these kernels in an obvious way. It's pretty non-trivial to work out the dictionary between these kernels from here and the kernels from there. And I think the key paper which made that possible is that one, Brödel, Dua, Dulat, Tancredi. They established dictionaries between different integration kernels for elliptic MPLs. And frankly, the higher genus version of the dictionary is an open problem. So I think that's a pretty pressing one, really interesting one. I wish I had a solution for that.
Thank you for the nice talk. I have a sweet feeling that I understood more than usual in this in this subject.
Pleasure to hear.
I wanted to ask you, once one sees the Lux connection which you wrote, I mean, Cartan-Moore or Lux, one wants to quantize it. Do you know, like we do, for example, in finite gap method, yes, this Lux connection is a starting point for quantization. So from classical curve to quantum spectral curve, etc. Could you imagine something like that here and some quantization of these polylogs, etc., or it's too exotic?
Oh, yeah, I heard people discuss that, yeah. I'm lacking the expertise to give you a qualified answer on the spot, but I think it could be an interesting research problem to try getting towards a higher genus Calogero-Moser system based on some of the ingredients here, but I wouldn't know how to do that.
Thank you.
There are a simplification for hyperelliptic curves compared to generic.
I fully agree, yeah. So that's a particular motivation to tackle the attempt to set up the dictionary in the near future. At genus 2, for instance, the natural integration kernels will also have a x squared dx over y, x cubed dx over y. I think a first step is to translate all of these into the Enriquez kernels in F tensors and to see what the simplifications are. I don't have much intuition about that. Or maybe Konstantin, can you comment?
So we also looked at periods over these polylogarithms, so A-cycle integrals. And there we see that there are certain identities which only appear for hyperelliptic curves. So there seems to be some special cases when you have an hyperelliptic curve instead of something which is not hyperelliptic. So I guess the hyperelliptic involution might play a role in simplifying things.
Thanks.
Okay, so if there's no more questions, let's thank Oliver again. Now I give it to him.
Okay, just a few words before we go. So Oliver was kind enough to thank some of the people who have been contributing to this the success of this workshop. But of course, there are others that we should also thank. As one of the organizers, I would like to ask you to join me in thanking first all of the speakers and all of the poster presenters of this workshop, of this conference. Without whom, of course, this would have been a very boring event. Then we've also had some other things that have happened during the week with panel discussions and presentations of the work of GenHet. I would like to thank everyone who has participated in that, in sharing their experiences with us. Then Oliver did thank the administrators here at Nordita and at COST, but I think we can give them another applause, in particular since they are in the room. So Jimmy and Olga and Elvira, thank you very much. Then I would like to thank all the chairs and all the people who have been running with microphones throughout the week. And I would also like to thank Watse for dealing with all the technicalities. And finally, last but definitely not least, thank you to all of the participants. There have been it's been so lovely to see all of the discussions and to hear that the discussions go on well, after even the last talk today. Thank you to all, and I would like to now say that, of course, this is not the end. Many of you will stay tomorrow for JoeFest, and that will be, of course, a great occasion to continue the scientific discussions. And then there's a future that Alessandro will now tell us about.
Thank you very much, Magdalena. And indeed, we are in the business of making predictions here, or we should be. And I can make some predictions about the next events which you might attend. And you see, you can find them all online. You don't have to take notes. They are on our website, theorychallenges.eu. And if you go under events, here are the 2026 events. And the first one will actually be the next Eurostring meeting. As you see, is going to be in Athens from the 4th to the 7th of May. So I hope really that everybody can come there. On top of this event, which is really of interest for the whole community, there are going to be other events that maybe are a bit more targeted to segments of our community. There is going to be a workshop on thermal CFT and black hole physics in Crete, again in Greece, in May. You find more information and also the local contact person on each of these events. So after that, in Munich, in a date that will be fixed soon, there is going to be another workshop, this time more focused about supergravity. And then there is going to be a conference in Wrocław, in Poland, and that will be in July. So for each of these events, you can contact either the working group leaders of the working groups indicated there or the local organizers if you want more information. And finally, there is going to be a school. This is going to be for PhD students, postdocs, maybe some very motivated master students. It's one of these young researcher schools that we organized in the past, and it's going to be in Budapest at the end of August, and it's going to be about integrability and conformal field theory and their relation for two-dimensional models. So I hope to see many of you at these events, and if you have any questions, of course, you can contact myself or the other organizer in COST. You find all the links on the website. Thank you very much again. Thank you very much for making this meeting a success, and see you maybe tomorrow at JoeFest or in Athens. Thank you very much.